Well, joining me now to give his take on our oceans becoming more acidic is Todd Capson. He's the Science and Policy Advisor to the Global Oceans Health Program. Todd, thanks for joining us again.
Thank you very much.
I want to ask you a bit more about this phenomenon of acidification. Why are acid levels rising?
They're rising in response to increasing CO2 levels. Humanity dumps roughly 100 tons per second of CO2 into the world's oceans. But that CO2 doesn't remain static. As your introduction mentioned, CO2 reacts with water, and that forms a weak acid. And that acid releases a hydrogen atom, but hydrogen atoms are very unhappy molecules, so they look for something to react with, and that something is carbonate. The problem with that is that's carbonate that is no longer available to form calcium carbonate, which is what oysters, all variety of shellfish, pteropods, corals, all sorts of organisms use to build their shells. So in effect, when CO2 enters the water, there is less carbonate available for any organism that needs a calcium carbonate shell.
So when you say we're dumping CO2 in bigger quantities now into the ocean, how are we doing that?
We're dumping it, well, there are a number of different sources. Deforestation is one. Certainly, the primary sources are emissions from our tailpipes, emissions from coal-fired plants, another example. We know, for example, at the beginning of the industrial period, the levels of CO2 were about 250 parts per million is the measure that we use. We've now exceeded 400. So we've roughly doubled the amount of CO2 in the atmosphere over the past 200 years. And what that amounts to is really an unprecedented experiment in the history of planet Earth. We can go back at the geological record, some 300 million years, and that's about as far back as you can go and really get reliable data and say, is there any time in the geological record that we can look at to get an idea of what we're in store for and what the response of the world's oceans might be? The closest we can get is about 55 million years ago, which over a period of 5,000 years, we doubled the CO2 levels. And that caused a massive extinction of small shelled organisms. And you could say, well, who cares about a small shelled organism? The problem with that is that these small organisms underpin many important food webs. So for example, the pteropods that we're losing now in the Arctic Ocean due to acidified waters, those are food for salmon, for whales, for seabirds, for all sorts of things. So we see these ripple up effects. But in effect, what we've done is we've done in 200 years what took 5,000 years to accomplish in the geological history. And even over 5,000 years, there were massive repercussions. So we've increased things at a rate of somewhere between 10 to 100 times faster. And that amounts to, in effect, an unprecedented experiment in the planet's history.
You know, the conventional belief for a long time was that it was better to have a great deal of carbon dioxide in the sea because that meant we had less carbon dioxide in the atmosphere. But that's wrong, isn't it?
That's very wrong. You're right, the oceans were doing us a big favor for a while by acting as what we call a sink for carbon dioxide, and we think that's great. And indeed, all that carbon dioxide going into the oceans has mitigated or relieved the massive impact of climate change. But we now know that that's coming at a huge expense because we're dumping in that CO2 so fast that the oceans don't really have a chance to respond. That's why we're seeing an increase in the hydrogen ion levels, and we've seen an increase in acidity of about 30%. But again, the important point to make, though, it's the increase in acidity is not a good thing. It has many bad repercussions, but where it really matters is the removal of carbonate for all those shell-building organisms, and that's why you so often hear this in the context of shellfish and corals and things of that nature.
Right, so we do know what ocean acidification is doing to organisms in the sea, life in the sea. How does it affect us on land?
Well, certainly, probably the best known example is what happened in the Pacific Northwest. We're starting in about 2007 and 2008. Shellfish hatcheries, and these hatcheries produce oyster seed, and then they sell that seed to shellfish farmers, which then grow those oysters. They lost 80% of their production starting in about 2007. And these are some of the most talented growers of seed anywhere on the planet. At the same time that happened, there were all sorts of other observations that didn't quite add up. For example, the pipes that bring in water from the adjacent inlet and that they use to fill their tanks are usually fouled. They have to go out there once every 6 months and chip away all the barnacles and mussels. And they went out to clean them, and they're clean. And they're looking at it and say, what's up with this? It was clear from all this anecdotal information that there were major changes in the world, in the oceans. What they ultimately figured out through a collaboration between government, scientists, and industry, and it's really, I want to stress that word partnerships, because that's really the only way we're going to wrap our head around this complex issue. They were able to determine that it was because of ocean acidification that they lost their shellfish production. So that's an industry worth thousands of dollars, 300 jobs, and that's just the Pacific Northwest. So you could ask the question, why the Pacific Northwest? Is there something special about that? There is a series of currents that tends to enrich CO2 levels. It's CO2 that we dumped into the ocean, but by the time it comes up to the surface, it's enriched right off the coast of the Pacific Northwest. And it was high enough such that the shellfish were no longer able to build their shells. So that's where the impacts have been most obvious. But it also, let's face it, the United States is a wealthy country. So we have the resources. We can go to the Pacific Northwest. We can figure out what's going on. You find those same sorts of currents. You find 2 of them off the coast of Africa. You want to find 1 off the coast of South America, the Humboldt. These support massive, huge fisheries of global importance. It's very likely that those areas are also being impacted. They just don't happen to be in countries where we have the resources, the scientific resources, to go out there and address it.
What about other parts of the world? I mean, I was thinking particularly of the polar areas.
Absolutely. That's a very good question. Cold water absorbs more CO2 than warm water. So naturally, both the North Pole and the South Pole and any cold water is going to absorb more CO2. And that's something you can measure. This is really chemistry 101. It's very, very basic stuff. What they have found, what was reported recently in the scientific literature, was that these pteropods that you mentioned in the introduction to this piece, which underpin key ecosystems for fish, salmon, birds, all sorts of things in these Arctic ecosystems, are already starting to dissolve. So this is not, there's no point in talking about just projection to 2100 of what might happen. Of course, we need to think about that. But the impacts of ocean acidification are here. It's crystal clear. And the other point I wanted to make is that the people who are really ringing the alarm bell are typically scientists. People like myself, other chemical oceanographers that see this and realize that this is a really bad idea for society. We need to get a handle on this.
You mentioned a global experiment and international cooperation to counter this problem. Climate change gets a lot of attention. Ocean acidification doesn't get as much attention. We don't hear about it that often. But what is taking place as far as international cooperation, as far as making people aware that this problem exists?
We have a lot of work to do to raise awareness about this issue, and I think this is...
Are there workshops being held? Or?
Oh, yes, there are. So it's like any complex environmental issue, we have to address this on multiple fronts. We have to work with policymakers, the general public. But more concretely, and getting back to some of my own work with my partners, we spent the month of December in New Zealand. New Zealand has a robust shellfish aquaculture industry, which they hope will be worth $1 billion New Zealand dollars by 2024. They saw the events unfolding in the Pacific Northwest, and they're very keen to future-proof this industry. So what we did was we put together an A-team from the Pacific Northwest, and we shipped them all down to New Zealand and presented to the government and to industry. I said, this is what happened up here. This is how we dealt with it, because the Pacific Northwest is another good case in that they were able to take adaptive measures. They made the investments to monitor ocean chemistry, and they said, okay, this is what's coming our way. We can adapt to this. And they have been able to rebuild their shellfish aquaculture industry. So it's important to note that there are things we can do as long as we have a handle on the information. But organizing that meeting in New Zealand, one of my colleagues, Alan Barton, he was the one that really first suggested in 2007, I think this might be an issue of ocean acidification. When he was talking to the government and industry from New Zealand, I could have dropped a pin and it would have resonated. People, all of a sudden, there was this look like, okay, I get it. And really a fundamental part of our work is to mobilize industry voices, because industry voices, I think, are just like it was industry from U.S. talking to industry in New Zealand, I think those same folks will be effective on statewide and national levels.
Okay, well, I hope the program works, Todd. We're going to have to leave it there. Todd Capson, thanks for joining.
Thank you very much for this opportunity.